Okay, so let's review what we were looking at last year. Last year we looked at position time graphs, velocity time graphs, and acceleration time graphs. And sometimes we had position time graphs like this, which were linear. And one thing that we saw last year was that the rise over the run, or in other words the slope, of a position time graph is equal to velocity. So the change in position, delta x, over delta t, is defined as the velocity. That was the definition. Likewise, we found for a velocity time graph that its rise over its run, its slope, defined the acceleration. And one other thing, we found that from a velocity time graph, the area underneath the curve, so let's say from here to here, so we'll call this t, and then we'll go delta t over, so this will be t plus delta t. This area I'm going to color in purple. We found out that that was the displacement. So the area is equal to delta x, the displacement. So that's what we studied last year in physics, and now we're going to expand upon that a little bit. So what happens if you don't have a nice linear relationship? Let's say you have more of a parabolic relationship. Or in other words, let's say that we have x of t, again this is a position time graph, is equal to, we know with linearizing this it's going to have to square this axis. So let's just say it's t squared plus c, some constant. That could be number 3, 4, whatever, some constant because it doesn't start at the origin. Okay. We found last year that if I draw a red secant line in here from this point to this point on the curve, that gives me the average velocity during that time interval of t to delta t, or t plus delta t. But what if I want to know what the instantaneous velocity is? Is that the same as the instantaneous velocity anywhere along the curve? Well, surely it's not, because down here the slope is very little, and up here it's much more. It's accelerating. In fact, there's only one location where the instantaneous velocity is the same as that secant line's slope, and that's right here in the very middle of that time interval. So how can I use this secant line in such a way that the slope of that secant line will be the same as, let's say I want to figure out what is the instantaneous velocity right here. Well, the only way to find the instantaneous velocity there is to use a tangent line. But let's just say I want to use a secant line. How can I use a secant line such that its slope will be the same approximately as this blue tangent line? Well, you can see it's kind of the same. It's similar. It's positive, but it's not the same. The only way I can bring it so it is the same is if I start bringing these points closer and closer together near this blue point here, and make it so that this time interval gets smaller and smaller. And so that's what we're going to look at. We're going to figure out, if I make this interval as small as possible, that the slope of that secant line approximates the slope of that tangent line. So for right now, let's just go ahead and find a slope of this nice red secant line here. And to do that, we know that slope is given by delta x over delta t for this displacement graph. So let's say we need to find what the coordinates of these two locations is at. So I know that the coordinate of that location is t plus, t evaluated, x evaluated t. That is the coordinate of that pair. That's the ordered pair there. I need to know, likewise, what is the ordered pair at that location. Well, notice I've moved from t over to t plus delta t. So that location is going to be t plus delta t. And it's going to be x evaluated at t plus delta t. So the slope ends up being my final x location, x evaluated at t plus delta t, minus x evaluated at t, all over the delta t, which is just delta t. Now remember what I'm trying to do. That is the slope of my secant line. What I want to do though is I want to make this delta t go vanishingly small to 0. By the way, this is what we did in the spreadsheet program. We actually took this interval so it was really small. It wasn't 0 though, it was 0.1 if you remember. You can look back if you want to. But I'm going to make it really small. And the notation I'm going to use is this. The limiting case where I take delta t to 0, it's going to be approaching 0. That width is going to be. Well, here's where I run into my first problem. Because you already know that when you divide any number by 0, you end up getting an undefined quantity for the slope. So that's the problem. A secant line has got to have 2 points on the curve, and when I take this to 0, it only ends up being 1 point. So what can I do? Well, at this point, it looks like this formula, even though it's correct, is not very useful. But what would happen if I go ahead and plug this ordered pair in over here? In other words, what if I evaluate x at t plus delta t? Well, that would be simply t plus delta t squared plus c. How does that help? Well, I'm going to plug that in right here and see if that ends up simplifying. I know dividing by 0 is not good, but what if I could cancel that out? Okay, so here what we've got is this slope equation for the secant line. And here are the 2 points, x evaluated at t and x evaluated at t plus delta t, that I'm going to be plugging in here. And so my slope becomes the following. Slope will be equal to the limit as delta t approaches 0 of plugging this in for this first quantity. I get t plus delta t squared plus c minus my x evaluated at t, which is t squared plus c, all over delta t. At first this appears to give me the same problem, but I'm going to FOIL this out in hopes that I can cancel the delta t, and that would solve my problem. So I FOIL that out. I get t squared plus 2t delta t plus delta t squared plus c minus t squared minus c, all over, and I forgot my limit, as delta t approaches 0, all over delta t. Now, let's see here. I've got the t squared that I can cancel with this minus t squared. I've got this plus c that I can cancel with this minus c. And now, notice I can cancel the delta t with this delta t and this delta t with the square. So that's what I'm going to do. Okay, so now the delta t canceled with the delta t here and the square. So I'm left with the slope being equal to the limit as delta t goes to 0 of the quantity 2t plus delta t. And it's at this point that I can use this delta t going to 0. Before, when I try to divide by 0, we know that's undefined. But now, I don't have that division. I can go ahead and plug in delta t here, and this whole quantity here goes to 0, and it ends up being the slope is equal to 2t. So remember, this was the slope of the position time graph, and we know that the slope of the position time graph is velocity. So now that we know the slope of the position time graph is velocity, and we just found it's equal to 2t, now let's go ahead and look at that velocity time graph. So here's the velocity time graph. And so it would look something like that. And let's go ahead and find the slope of this. Now, of course, finding the slope of this is pretty easy. It's going to be delta v over delta t. And so the slope, we know, is going to be acceleration. and it's going to be the instantaneous acceleration, and in this case, delta v over delta t. Now that should be easy because we just found that the velocity as a function of time is equal to, or the instantaneous velocity, is equal to 2t. Well, that should be pretty easy to figure out the slope. In fact, we know what that is, and I'm not going to say it because I know you know what it is. I'm going to go ahead and use this same idea that we did here that was pretty complicated, and see if it works, and see if it gives us the answer that we know full well what that slope is. So in other words, we know that the slope is equal to the change in velocity over change in time, which, let's set that equal to the limit as delta t goes to 0. So we've got this delta t here, let's take it to 0. So we're trying to find the slope of the tangent line of that, which will be the same as the slope of that, since it's linear. Okay, so for this, we would want to know what the velocity at t plus delta t is, and subtract the velocity at just t divided by delta t. Again, we have this problem of we're dividing by delta t, which is going to give us undefined when we take delta t to 0. But let's go ahead and plug in what the velocity at t plus delta t right here would be. For that, it would be equal to limit as delta t goes to 0. The velocity at that point would just be plugging t delta t into this equation here. So it's going to be 2 times the quantity t plus delta t minus the velocity at this point, and that would just simply be 2t. And I'm going to divide that by delta t. Again, I have the problem I can't divide by 0, I get undefined, but maybe by multiplying this out, it'll simplify. So limit delta t goes to 0 of 2t plus 2 delta t minus 2t over delta t. The 2t and the minus 2t cancel. The delta t cancels with the delta t. So there is no delta t to worry about going to 0. I just get this to be equal to 2. So the slope of this velocity time graph, which is the acceleration, change velocity over change of time, is equal to 2 with this long drawn out process, which we already knew the slope of this equation was 2. So it confirms to us that this long drawn out process does give us the right idea. And so this is the acceleration, instantaneous acceleration.